As we have discussed in previous videos, neural networks simulate the human brain by processing information through artificial neurons or nodes. They learn by considering examples and typically don't rely on task-specific programming. We developed this video for anyone looking to make an informed business decision or anyone wanting to understand how AI can best be used in daily life. We are not going to discuss the programming or mathematics of the process. So, how exactly does a neural network learn? A neural network learns through a process of backward propagation of errors, or backpropagation. To understand backpropagation, first remember that a neural network's output is a prediction with the highest probability of addressing the input. To start the backpropagation process, the network is first given an input with a known or expected output, then processed to develop an output called a predicted output. The predicted output is then compared to the expected output. The difference between the predicted and expected output is then calculated. Using this difference, or the error, the neural network then works backwards to make changes that reduce the error. After the changes are made, the process starts all over again, on and on, repeating this cycle of calculating the error, then correcting for it. With each cycle, the error gets smaller and smaller. Thus, the network is learning because with each iteration, the network has a higher probability of providing the correct output. Building on this base understanding, let's discuss how backpropagation works in more detail. Backpropagation follows what you would expect as a logical order. It starts with a forward pass where input data are processed in the network to an output. The difference between the observed output and the expected output is then quantified as an error. There are several common techniques for doing this, but that is beyond the scope of today. Next, the backward pass starts by retracing the steps of the forward pass. The initial step is to understand the contribution of the output layer to the error. To do this, an error gradient is calculated for each neuron in the output layer. An error gradient is a measure of how a change at a parameter, in this case an individual neuron, will impact the final error. Knowledge of the error gradient is important because it will direct the eventual changes to the network. Next, the error is then propagated backward through the network. In each layer, an error gradient for both the neurons and the weights is calculated. This gradient measures how changes in weights in neurons within a layer will impact the overall error. Here the focus is on understanding how the entire layer contributes to the error. Next, an error gradient is calculated for the individual weights and biases of each neuron. If you remember from previous videos, weights and biases are the adjustable parameters within the neural network. By developing an error gradient for each weight and bias, the network is now able to make a precise adjustment of these parameters at each neuron. In the final step, the weights and biases in each layer are adjusted based on the gradient. This is in essence the learning phase, as the weights and biases are adjusted in the opposite direction of the error gradient to reduce the output error. Now, the process is repeated over and over again. With each iteration, the network is gradually learning and in doing so reducing the output error. As you would anticipate, there can be several issues encountered during backpropagation. The most likely challenges to occur are vanishing gradients, exploding gradients, overfitting, and underfitting. A vanishing gradient occurs when the gradients become very small, effectively preventing the weights and biases of the initial layers from being updated significantly during training. The consequence is that these layers learn very slowly, hindering the overall training of the network and the model's ability to develop a good solution. An exploding gradient arises when the gradients become excessively large. Such large gradients can lead to very large updates to the network weights during training, causing the model's learning process to become unstable. This instability often leads to divergence, meaning the network fails to converge to a solution and cannot learn effectively from the training data. In networks with multiple hidden layers, the problem can be exacerbated, as the gradients can increase exponentially when multiple large derivatives are multiplied together through the layers. Overfitting is a common issue where the model learns the details and noise in the training data to an extent that it negatively impacts the performance of the model on new, unseen data. When overfitting occurs, the network performs exceptionally well on the training data, capturing even minor fluctuations, but fails to generalize to new data. This can be due to a variety of factors, including having too complex a model relative to the simplicity of the data. training the model for too long, or not having enough data to train on. Underfitting occurs when a model is too simple to capture the complexities of the data it is trained on. This can happen for several reasons, such as having too few parameters in the model, making it overly simplistic, using inappropriate or insufficiently powerful model architectures, or not training the model with enough iterations. Underfitting is characterized by poor performance, not just on validation or test data, but also on the training data itself, indicating that the model has not learned the underlying patterns in the data well. It often results from high bias in the model, where bias refers to the error due to overly simplistic assumptions in the learning algorithm. So, there you have it, an introduction to backpropagation in neural networks. I would suggest the following as 3 takeaways from the video. 1. Backpropagation is a central mechanism in neural network training. It involves adjusting the network's weights and biases based on the error between the network's predicted output and the actual desired output. This iterative process is essential for the network to learn from the training data. 2. Backpropagation involves the calculation of the error gradient for each neuron, which quantifies how the overall error is impacted by a change at an individual neuron and is used to update the network's weights. And finally, 3. Backpropagation involves the iterative process of making small adjustments to the weights and biases based on the aggregated feedback from the entire dataset, gradually improving the network's performance and reliability in predictions. I hope you enjoyed the video. If you have not already done so, take a look at our other videos on neural networks. Thanks for watching.